Chapter 15, Handling Events. You have power over your mind, not outside events. Realize this and you will find strength. Marcus Aurelius, Meditations. Some programs work with direct user input, such as mouse and keyboard actions. That kind of input isn't available ahead of time. As a well-organized data structure, it comes in piece by piece in real time, and the program must respond to it as it happens. Event handlers. Imagine an interface where the only way to find out whether a key on the keyboard is being pressed is to read the current state of that key. To be able to react to key presses, you would have to constantly read the key's state to catch it before it's released again. It would be dangerous to perform other time-intensive computations since you might miss a key press. Some primitive machines handle input like this. A step up from this is for the hardware or operating system to notice the key press and put it in a queue. A program can then periodically check the queue for new events and react to what it finds there. Of course, the program has to remember to look at the queue and to do it often, because any time between the key being pressed and the program noticing the event will cause the software to feel unresponsive. This approach is called polling. Most programmers prefer to avoid it. A better mechanism is for the system to actively notify the code when an event occurs. Browsers do this by allowing us to register functions as handlers for specific events. The window binding refers to a built-in object provided by the browser. It represents the browser window that contains the document. Calling its addEventListener method registers the second argument to be called whenever the event described by its first argument occurs. Events and DOM nodes. Each browser event handler is registered in a context. In the previous example, we called addEventListener on the window object to register a handler for the whole window. Such a method can also be found on DOM elements and some other types of objects. Event listeners are called only when the event happens in the context of the object on which they are registered. That example attaches a handler to the button node. Click on the button causes the handler to run, but clicks on the rest of the document do not. Given a node, an onClick attribute has a similar effect. This works for most types of events, and you can attach a handler through the attribute whose name is the event with on in front of it. But a node can only have one onClick attribute, so you can register only one handler per node that way. The addEventListener method allows you to add any number of handlers, meaning it's safe to add handlers even if there is already another handler on the element. The removeEventListener method, called with arguments similar to addEventListener, removes a handler. The function given to removeEventListener has to be the same function value given to addEventListener. When you need to unregister a handler, you'll want to give the handler function name once in the example to be able to pass the same function value to both methods. Event objects. Though we've ignored it so far, event handler functions are passed an argument, the event object. This object holds additional information about the event. For example, if we want to know which mouse button was pressed, we can look at the event object's button property. The information stored in an event object differs per type of event. We'll discuss different types later in the chapter. The object's type property always holds a string identifying the event, such as click or mouse down. Propagation. For most event types, handlers registered on nodes with children will also receive events that happen in the children. If a button inside a paragraph is clicked, event handlers on the paragraph will also see the click event. But if both the paragraph and the button have a handler, the more specific handler, the one on the button, gets to go first. The event is said to propagate outward from the node where it happened to the node's parent node, and so on to the root of the document. Finally, after all handlers registered on a specific node have had their turn, handlers registered on the whole window get a chance to respond to the event. At any point, an event handler can call the stop propagation method on the event object to prevent handlers further up from receiving the event. This can be useful when, for example, you have a button inside another clickable element and you don't want clicks on the button to activate the outer element's click behavior. The following example registers mouse down handlers on both a button and the paragraph around it. When clicked with the right mouse button, the handler for the button calls stop propagation, which will prevent the handler on the paragraph from running. When the button is clicked with another mouse button, both handlers will run. Most event objects have a target property that refers to the node where they originated. You can use this property to ensure that you're not accidentally handling something that propagated up from a node you do not want to handle. It's also possible to use a target property to cast a wide net for a specific type of event. For example, if you have a node containing a long list of buttons, it may be more convenient to register a single click handler on the outer node and have it use a target property to figure out whether a button was clicked, rather than registering individual handlers on all of the buttons. Default actions. Many events have a default action. If you click a link, you'll be taken to the link's target. If you press the down arrow, the browser will scroll the page down. If you right-click, you'll get a context menu, and so on. For most types of events, the JavaScript event handlers are called before the default behavior takes place. If the handler doesn't want this normal behavior to happen, typically because it has already taken care of handling the event, it can call the prevent default method on the event object. This can be used to implement your own keyboard shortcuts or context menu. It can also be used to obnoxiously interfere with the behavior that users expect. For example, here's a link that cannot be followed. Try not to do such things without a really good reason. It'll be unpleasant for people who use your page when expected behavior is broken. Depending on the browser, some events can't be intercepted at all. On Chrome, for example, the keyboard shortcut to close the current tab, Ctrl-W or Command-W, cannot be handled by JavaScript. Key events. When a key on the keyboard is pressed, your browser fires a key down event. When it's released, you get a key up event. Despite the name, key down fires not only when the key is physically pushed down. When a key is pressed and held, the event fires again every time the key repeats. Sometimes you have to be careful about this. For example, if you add a button to the DOM when a key is pressed and remove it again when the key is released, you might accidentally add hundreds of buttons when the key is held down longer. The previous example looks at the key property of the event object to see which key the event is about. This property holds a string that, for most keys, corresponds to the thing that pressing the key would type. For special keys, such as enter, it holds a string that names the key, enter in this case. If you hold shift while pressing a key, that might also influence the name of the key. V becomes V, 1 may become exclamation mark, if that's what pressing shift 1 produces on your keyboard. Modifier keys such as shift, control, alt, and meta, command on Mac, generate key events just like normal keys. When looking for key combinations, you can also find out whether those keys are held down by looking at the shift key, control key, alt key, and meta key properties of keyboard and mouse events. The DOM node where a key event originates depends upon the element that has the focus when the key is pressed. Most nodes cannot have focus unless you give them a tab index attribute, but things like links, buttons, and form fields can. We'll come back to form fields in Chapter 18, when nothing in particular has focus. Document.body acts as the target node of key events. When the user is typing text, using key elements to figure out what is being typed is problematic. Some platforms, most notably the virtual keyboard on Android phones, don't fire key events. But when you have an old-fashioned keyboard, some types of text input don't match key presses in a straightforward way, such as an input method editor, IME software, used by people whose scripts don't fit on a keyboard, where multiple keystrokes are combined to create characters. To notice when something was typed, elements that you can type into, such as the input and text area tags, fire input events wherever the user changes their context. To get the actual content that was typed, it's best to directly read it from the focus field, which we discussed in Chapter 18. Pointer events. There are currently two widely used ways to point at things on a screen: mice, including devices that act like mice, such as touchpads and trackballs, and touchscreens. These produce different types of events. Mouse clicks. Pressing a mouse button causes a number of events to fire. The mouse down and mouse up events are similar to key down and key up, and fire when the button is pressed and released. These happen on the DOM nodes that are immediately below the mouse pointer when the event occurs. After the mouse up event, a click event fires for most specific node that contain both the press and the release of the button. For example, if I press down the mouse button on one paragraph and then move the pointer to another paragraph and release the button, the click event will happen on the element that contains both these paragraphs. If two clicks happen together, a double click event also fires after the second click event. To get precise information about the place where a mouse event happened, you have to look at its client X and client Y properties, which contain the event's coordinates in pixels relative to the upper left corner of the window, or page X and page Y, which are relative to the upper left corner of the whole document, which may be different when the window has been scrolled. The following program implements a primitive drawing application. Every time you click the document, it adds a dot under your mouse pointer. We'll create a less primitive drawing application in Chapter 19. Mouse motion. Every time a mouse pointer moves, a mouse move event fires. This event can be used to track position of the mouse. A common situation in which this is useful is when implementing some sort of mouse dragging functionality. As an example, the following program displays a bar and sets up event handlers so that dragging to the left or right on this bar makes it narrower or wider. Note that the mouse move handler is registered on the whole window. Even if the mouse goes outside the bar during resizing, as long as the button is held, we still want to update its size. We must stop resizing the bar when the mouse button is released. For that, we can use the buttons property, note the plural, which tells us about the buttons that are currently held down. When it is 0, no buttons are down. When buttons are held, the value of the buttons property is the sum of the codes for those buttons. The left button has code 1, the right button 2, the middle one 4. With the left and right buttons held, for example, the value of buttons will be 3. Note that the order of these codes is different from the one used by button, where the middle button came before the right one. As mentioned, consistency is a strong point of browser programming interface. Touch events. The style of graphical browser that we use was designed with mouse interfaces in mind, at a time where touchscreens were rare. To make the web work on early touchscreen phones, browsers for these devices pretended to a certain extent that touch events were mouse events. If you tap your screen, you'll get a mouse down, mouse up, and click events. But this illusion isn't very robust. A touchscreen doesn't work like a mouse. It doesn't have multiple buttons, you can't track the finger when it isn't on the screen to simulate mouse move, and allows multiple fingers to be on the screen at the same time. Mouse events cover touch integration only in straightforward cases. If you add a click handler to a button, touch users will still be able to use it, but something like the resizable bar in the previous example does not work on a touchscreen. There are specific event types fired by touch interaction. When a finger starts touching a screen, you get a touch start event. When it is moved while touching, touch move events fire. Finally, when it stops touching the screen, you see a touch end event. Because many touchscreens can detect multiple fingers at the same time, these events don't have a single set of coordinates associated with them. Rather, their event objects have a touches property, which holds an array-like object of points, each of which has its own client X, client Y, page X, and page Y properties. You could do something like this to show red circles around every touching finger. You'll often want to call prevent default and touch event handlers to override the browser's default behavior, which may include scrolling the page on swiping, and to prevent the mouse events from being fired, for which you may also have a handler. Scroll events. Whenever an element is scrolled, a scroll event is fired on it. This has various uses, such as knowing what the user is currently looking at for disabling off-screen animations or sending spy reports to your evil headquarters, or showing some indication of progress by highlighting parts of a table of contents or showing a page number. The following example draws a progress bar above the document and updates it to fill up as you scroll down. Giving an element a position of fixed acts much like an absolute position, but also prevents it from scrolling along with the rest of the document. The effect is to make our progress bar stay at the top. Its width is changed to indicate the current progress. We use % rather than px as a width when setting the width so that the element is sized relative to the page width. The global inner height binding gives us the height of the window, which we must subtract from the total scrollable height. You can't keep scrolling when you hit the bottom of the document. There's also an inner width of the window width. By dividing page Y offset, the current scroll position, by the maximum scroll position and multiplying by 100, we get the percentage for the progress bar. Calling prevent default on a scroll event does not prevent the scrolling from happening. In fact, the event handler is called only after the scrolling takes place. Focus events. When an element gains focus, the browser fires a focus event on it. When it loses focus, the element gets a blur event. Unlike the events discussed earlier, these two events do not propagate. A handler on the parent element is not notified when a child element gains or loses focus. The following example displays help text for the text field that currently has focus. The window object will receive focus and blur events when the user moves from or to the browser tab or window in which the document is shown. Load event. When a page finishes loading, the load event fires on the window and the document body objects. This is often used to schedule initialization actions that require the whole document to have been built. Remember that the content of script tags is run immediately when the tag is encountered. This may be too soon, for example when the script needs to do something with parts of the document that appear after the script tag. Elements such as images and script tags that load on an external file also have a load element that indicates the files they reference were loaded. Like the focus-related events, loading events do not propagate. When you close page or navigate away from it, for example by following a link, a before unload event fires. The main use of this event is to prevent the user from accidentally losing work by closing a document. If you prevent the default behavior on this event and set the return value property on the event object of a string, the browser will show the user a dialog asking if they really want to leave the page. That dialog might include your string, but because some malicious sites try to use these dialogs to confuse people into staying on their page to look at dodgy weight loss ads, most browsers no longer display them. Events and the event loop. In the context of the event loop, as discussed in Chapter 11, browser event handlers behave like any other asynchronous notifications. They are scheduled when the event occurs, but must wait for the other scripts that are running to finish before they get a chance to run. The fact that events can be processed only when nothing else is running means that if the event loop is tied up with other work, any interaction on the page which happens through events will be delayed until there's time to process it. So if you schedule too much work, either with long-running event handlers or with lots of short-running ones, the page will become slow and cumbersome to use. For cases where you really want to do some time-consuming thing in the background without freezing the page, browsers provide something called web workers. A worker is a JavaScript process that runs alongside the main script on its own timeline. Imagine that squaring a number is a heavy long-running computation that we want to perform in a separate thread. We could write a file called code squareworker.js that responds to messages by computing a square and sending the message back. To avoid the problem of having multiple threads touching the same data, workers do not share their global scope or any other data with the main script's environment. Instead, you have to communicate with them by sending messages back and forth. This code spawns a worker running that script, sends it a few messages, and outputs the responses. The post-message function sends a message which will cause a message event to fire in the receiver. The script that created the worker sends the receives messages through the worker object, whereas the worker talks to the script that created it by sending and listening directly to its global scope. Only values that can be represented as JSON can be sent as messages. The other side will receive a copy of them rather than the value itself. Timers. The setTimeout function we saw in Chapter 11 schedules another function to be called later, after a given number of milliseconds. Sometimes you need to cancel a function you have scheduled. You can do this by storing the value, returning by setTimeout, and calling clearTimeout on it. The cancel animation frame function works in the same way as clearTimeout. Calling it on a value returned by request animation frame will cancel that frame, assuming it hasn't already been called. A similar set of functions, setInterval and clearInterval, are used to set timers that should repeat every X milliseconds. Debouncing. Some type of events have the potential to fire rapidly many times in a row, such as the mouse move and scroll events. When handling such events, you must be careful not to do anything too time-consuming, or your handler will take up so much time that interaction with the document starts to feel slow. If you do need to do something non-trivial in such a handler, you can use setTimeout to make sure you're not doing it too often. This is usually called debouncing the event. There are several slightly different approaches to this. For example, suppose we want to react when the user has typed something, but we don't want to do it immediately for every input event. When they are typing quickly, we just want to wait until a pause occurs. Instead of immediately performing an action on the event handler, we set a timeout. We also clear the previous timeout, if any, so that when the events occur close together, closer than our timeout delay, the timeout from the previous event will be cancelled. Given an undefined value to clear timeout or calling it on a timeout that has already fired has no effect. Thus, we don't have to be careful about when to call it and when we simply do so for every event. We can use a slightly different pattern if we want to space responses so that they're separated by at least a certain length of time, but want to fire them during a series of events, not just afterwards. For example, we might want to respond to mouse move events by showing the current coordinates of the mouse, but only every 250 milliseconds. Summary. Event handlers make it possible to detect and react to events happening in our web page. The addEventListener method is used to register such a handler. Each event has a type, key down, focus, and so on that identifies it. Most events are called in specific DOM elements and then propagate to that element's ancestors, allowing handlers associated with those elements to handle them. When an event's handler is called, it's passed an event object with an additional information about that event. This object also has methods that allow us to stop propagation, and prevent the browser's default handling of the event, prevent default. Pressing a key fires key down and key up events. Pressing a mouse button fires mouse down, mouse up, and click events. Moving the mouse fires mouse move events. Touchscreen interactions will result in touch start, touch move, and touch end events. Scrolling can be detected with the scroll event, and focus changes can be detected with the focus and blur events. When the document finishes loading, a load event fires on the window. Exercises. Balloon. Write a page that displays a balloon using the balloon emoji. When you press the up arrow, it should inflate, grow 10%. When you press the down arrow, it should deflate, shrink 10%. You can control the size of text, emojis or text, by setting the font size CSS property style.fontSize on its parent element. Remember to include a unit in the value, for example, pixels 10px. The key names of the arrow keys are arrow up and arrow down. Make sure the keys change only the balloon without scrolling the page. Once you have that working, add a feature where if you blow up the balloon past a certain size, it explodes. In this case, exploding means that it is replaced with an explosion emoji, and the event handler is removed so that you can't inflate or deflate the explosion. Mouse trail. In JavaScript's early days, which was the high time of gaudy home pages with lots of animated images, people came up with some truly inspiring ways to use the language. One of these was the mouse trail, a series of elements that would follow the mouse pointer as you moved it across the page. In this exercise, I want you to implement a mouse trail. Use absolutely positioned div elements with a fixed size and background color referred to the code in the mouse click section, for example. Create a bunch of these elements, and when the mouse moves, display them in the wake of the mouse pointer. There are various possible approaches here. You can make your trail as simple or as complex as you want. A simple solution to start with is to keep a fixed number of trail elements and cycle through them, moving the next one to the mouse's current position every time a mouse move event occurs. Tabs. Tabbed panels are common in user interfaces. They allow you to set an interface panel by choosing from a number of tabs sticking out above an element. Implement a simple tabbed interface. Write a function as tabs that takes a DOM node and creates a tabbed interface showing the child elements of that node. It should insert a list of button elements at the top of that node, one for each child element, containing text retrieved from the data tab name attribute of the child. All but one of the original children should be hidden, given a display style of none. The currently visible node can be selected by clicking the buttons. When that works, extend it to the style of the button for the currently selected tab differently so that it is obvious which tab is selected.